All right, so we'll continue looking at a few examples now of indeterminate forms and how we can figure out these limits either with or without L'Hopital's rule. So for our first one, if we take that pi from the left and we plug it in, you would get a 0 times infinity, which if you look back at our list from the last video, that is truly an indeterminate form. And if our goal is to get a 0 over 0 or an infinity over infinity, we need to construct a numerator and a denominator. In this case, it's not really going to be too bad. If I take my tangent and apply the reciprocal identity, we have a cotangent now of x over 2. So now, again, if I plug in, and I think I wrote a -1 there, that should just be from the left. If I plug in the pi from the left here, this is going to give us a 0 over 0 indeterminate form, one that is acceptable using L'Hopital's rule. So now, LH for L'Hopital's rule, copy that limit notation down, pi from the left, and then using our derivative of the top, which is 1, and our derivative of the bottom, is going to be a -1/2 cosecant squared x over 2. Now we're ready to reevaluate. If I evaluate at pi from the left into cosecant squared of this thing, that quantity there goes to 1, leaving us with our final answer now of -2. So a little bit of trig and the reciprocal identity was really helpful in getting us into the correct form. From there, derivative of the numerator separately, derivative of the denominator separately, and then reevaluate, coming up with -2. Okay, so for this example, we'll start the same way. It's an infinity, so you can't plug it in directly, but view it as a large number. If you view it as a large number, this part goes to 0, and so we would have a 1 raised to the infinity. So a 1 raised to the infinity. Now that is one of our indeterminate forms, but we're going to need to manipulate it so that we can hopefully then use L'Hopital's rule. So now for this particular one, we're going to take a unique approach, one that's actually pretty common, but it's not obvious. I'll definitely go that far. So I'm going to say that y is equal to 1 plus 1 over x to the x. Okay, that was our function. Y equals f of x is this guy. I'm actually going to now natural log both sides. If I natural log this, this is going to give me the opportunity to take this x and bring it down. So we've got the natural log of y equals x times the natural log of 1 plus 1 over x. Now, before I really go much further, I'm going to put a big star next to this. Now, I'm doing it in a different color, so it's going to be a little easier for me to remember. But when we get our final answer, we have to remember to undo the logarithm. And so the inverse of the log would be the exponential. So we're going to, in fact, have to e whatever our answer comes out to be for that limit. Okay, so that's what that star is going to represent. We'll come back and discuss it here at the end so I don't forget. All right, so from there, now I'm looking at the limit as x approaches positive infinity of x times the natural log 1 plus 1 over x. Now, if you plug this stuff in, you actually end up with, once again, the infinity times the natural log of 1, which would be 0. You end up with infinity times 0. Well, that infinity times 0 is also an indeterminate form, but not one that we can use L'Hopital's rule on. So how can we construct this in such a way where we have that numerator and denominator? Well, this is where, again, once you see it, you'll know when to use it, but coming up with it on your own I wouldn't call obvious. So what I've done is I've left this alone in the numerator, but then if you look carefully at this denominator, the way I've written it, this is in fact the same thing as the natural log times the x. And by doing this, now you can see when we evaluate at a big number, we would get a 0 over a 0. So that was a big move in getting us into a form that we can use L'Hopital's rule. Okay, so I'll go ahead now, LH for L'Hopital, and we're going to have now 1 over 1 plus 1 over x, back times the derivative of the inside, divided by the derivative of the denominator separately, which would be a minus 1 over x squared. Conveniently, these two things go away, and really all we're left now to evaluate is that right there. And as x goes to infinity, this goes to 0, leaving us with just a 1 for our final answer. Now, kind of. 1 is the final answer of what I have drawn on my paper, but I can't forget that I got there by logging the function. So to undo the logarithm, we're going to e the result. So we would have now e to the first as our final answer. Okay? So remember, if I come up here and I e this, now it takes us back then to the original. Okay, so that's a pretty common technique, one that again I wouldn't call obvious, but now that you've seen it, hopefully you can apply it accordingly. All right, so for this one, we're going to start off the same way. We're going to plug in the 0. If we plug in that 0, we end up with our 0 raised to the 0 indeterminate form. To try to get it in a place where we can use L'Hopital's rule, much like the last problem, I'm going to let y equal tangent of 2x raised to the x. I'm going to natural log both sides. And then I'm going to bring the x down. So at this point, I'm going to put that big green X on my paper to remind myself at the end that I'm going to have to E both sides, meaning I'm going to have to take my answer and with a base E raised to that answer. Okay, so again, we'll circle back on that and talk about it like we did in the last one. But for right now, I'm ready to go ahead now and take the limit as X goes to 0 from the right of our X natural log tangent of 2x. So now, before we evaluate, let's kind of talk through this. We know that that's going to go to 0. We know that tangent of 0 is 0, and then the natural log of 0 goes off to an infinity. So for us, what we have is a 0 times infinity. Well, again, we kind of need that numerator and denominator distinctly, so I'll go ahead and apply that same technique I did a moment ago, where I'll leave that natural log in the numerator, but that x I'm going to write in the denominator as 1 over x. And in this case now, when you plug in the 0, this guy still is your infinity, and then in my denominator, when I plug a 0 in, 1 over 0 from the right, that's also going to be one of your infinities. So we have now finally hit our infinity over infinity. Okay, so that being said, now we can go ahead and use L'Hopital's rule. So I'll mark the LH for L'Hopital's rule. We'll have the limit as x approaches 0 from the right. The derivative of our numerator would be 1 over tangent of 2x times secant squared of 2x times 2. And then of our denominator, we would have minus 1 over x squared. So again, let's run through that numerator's derivative real quick. We've got 1 over tangent, then the derivative of the inside would be secant squared, then the derivative of the inside would be the 2. So that's separate, then the denominator separate would be minus 1 over x squared. Now this one can be cleaned up, and you can certainly play around with this however you so feel, but there are definitely other ways to go about it, but I've found the easiest way to look at this one now is the limit as x goes to 0 from the right of negative 4 times x squared over sine of 4x. So that whole thing cleans up to what I have right there. And so you can almost treat that like a trig identity. Pause the video and then you can confirm that. So now we're ready to reevaluate. We'll plug in 0 from the right, top and bottom. And from here, you get a 0 over 0, which is also an appropriate L'Hopital indeterminate form. So I'm going to need to continue and do another iteration. So in our numerator, we'll have our negative 8x. In our denominator, this would be a 4 cosine of 4x when you take the derivative of that denominator. Now when you plug in the 0, you can see in the denominator here, when you plug in a 0, this goes to 1, so we'd have a 4, but in the numerator we would have a 0. So 0 over 4 would go to 0. But now remember, that's not our answer. Because we had to log it, now we have to e it at the end. So e to the 0 would equal 1. So the final answer for our original limit is going to equal 1.